Okay, so we are back, and as I promised, we are going to have some fun with these three classes, and I am going to use group action to solve one problem. First, let me ask you the problem. We have three inverted cups, and at one time I can pick two of them and change their orientation. So if they are inverted, I can make them upright, and then keep doing like that. I take any of them, maybe these, but I am back. So my purpose is to make all three of them upright by doing so. And I am just trying it, and I am trying hard. It's not happening. I can't do that. I have tried maybe a couple of times, 10 times or something, but even if you try 1,000 times, it's not going to happen. And why is it the case? Why I can't make all three of them upright? So that's a question. For that, let me first convince you that there is some group action which is going on here. So whenever there is group action, there is a group and then there is a set. So this is one configuration. How many such configurations are possible? These are three, and there are two positions for each of these classes. 2 to the power 3, 8 configurations are possible, and as I had indicated in the last lecture, look at it. This sequence of zeros and ones, there is some similarity, right? So we can say that 0 is the inverted position, and say 1 is the upright position. So this set, which we constructed as a group, just take it as a set. This is set of all configurations which are possible for these three classes. So this is set of all configurations, all possible configurations. And on the set of configurations, what is acting? Well, I am acting, right? It's a group. There is a group which is acting, which is changing these configurations. So here is an interesting idea. You consider the same. You remember Klein's 4 group, as I have been mentioning, and this time you denote it by 1, A, B, C. There are 4 elements in this group. As you recall, A square is identity, B square is identity, C square is identity, and then AB is C, AC is B, and BC is A. So it's a abelian group, so ABC is same as BA, similarly this is same as CA and same as CB. Of course, A square, B square, C square is identity. So what I am saying is that this group has something to do with this problem. So I define the group action exactly in the same way as I am playing this game. V4 is acting on X. What is X? X is all possible configurations, and then there should be an action. So let's pick an element from V4. Well, if the element is identity, then whatever I pick from X, I'll pick something like say 101, or then it is simply 101. Nothing is happening. Interesting thing is, for example, when I pick A from V4, and then what is its effect on say 100? That's what I am going to explain. So effect of A on 100 is that this position, so let's call it position A, position B, position C. So position A is unchanged while two other positions are swapped. So 0 becomes 1, 1 becomes 0. So 1 0 0 becomes 1 1 1. So if I have this to be 1, 1 is upright position, 0 is inverted position. So if A is 1 and B is 0 and C is 1. So if I have this, then identity is not doing anything to it. Yeah, and here say 1 0 0, so it's 1 A 0 and C 0. So when I apply on this configuration the element A from the clans 4 group, what happens? All three become upright. So I don't touch A, I touch only other two and I just change their position. So all three become upright. If I take something else, say I take say B and consider how B is going to act with say 1 1 0. So I am not supposed to touch sorry. So I am not supposed to touch B. So this one will remain intact while the two other will be swapped. So 1 becomes 0 and this 0 becomes 1. So it becomes 0 1 1. So let us see. So the 1 1 0 meaning A is upright, B is upright, C is inverted. And when B is acting on 1 1 0, so I am just fixing this, I am not touching it, and other two I will just swap. So what I have is therefore 0 1 1. Yeah. So this is how we define the action, but be careful. So exercise for you is that this is actually an action. And I guess you remember the definition of action. So if I define the action of clients 4 group, action of V4 on this set of 8 elements, then it is actually an action. Okay. Now the question is, well, let's see number of orbits. How many orbits are there? That would be something interesting. So we will estimate the number of orbits for this action. So I consider say 0 0 0. That is all the elements are all three glasses are inverted. So I am looking at orbits of this action. So when all three glasses are inverted, action of 1 is again all three glasses are inverted. Action of A on 0 0 0 is first position becomes 1, sorry. So action of A is first position remains unchanged and 2 are changed. What about B? When B acts on 0 0 0, what happens? You have the middle position does not change and this changes to 1, this also changes to 1. And when it happens with C, what you have? Last position doesn't change and first two positions change. So 0 0 0 can move to either of these positions. What about 1 1 1? Under the influence of 1, 1, 1, 1 goes to simply 1, 1, 1, no change. What about A acting on 1, 1, 1? That is simply the position of A. The first position does not change, other two positions become 0. What about B acting on 1, 1, 1? Simply this does not change and these two things change. And C, you have this position C does not change while other two positions change. So orbit of 1, 1, 1 has these 4 elements. Fine. Let's see how many orbits are there. In this action. So average number of fixed points. So I pick 1. So I take element of G, and number of fixed points. So I take identity. Identity fixes everything, right? So I am using the fact that number of orbits is equal to average number of fixed points, as I have explained in previous lectures. What if I pick A? How many elements are fixed? So let's see. If A acts on anything, it's not going to be fixed, right? Because other two positions will change. So number of fixed points is 0. Same is true with B and same is true with C. Therefore, number of orbits is 1 divided by size of V4, which is 4, and number of fixed points, you just add them, which is just 2. So this action has 2 orbits and we have already identified this orbit and we have identified this orbit, and that's all. This covers all the elements of X. So there are 2 orbits, these 4 elements are in one orbit, these 4 elements are in one orbit, and therefore orbit of 0, 0, 0 is not same as orbit of 1, 1, 1. Therefore, by means of this action, therefore by the rules of this game, we cannot change the position where all 3 cups are inverted to position where all 3 cups are upright. So that's very interesting application of group actions. The same thing, the same problem we could have understood in much simpler terms, not even in terms of group actions, but using the concept of parity. So another explanation to this would have been using parity. So the notion of parity is something that we are going to learn. So let's see in this case what would parity mean. So here to each state I can assign parity in the following sense. So suppose these are 3 positions for the 3 cups A, B, C. This is inverted, so this is the notation inverted. This is notation for upright. So whenever I have this down, I say 1. When I have upright, I say -1. So X is a set of all configurations. So size of X is 8, and this map goes, parity maps goes from X to say 1 minus 1, and what it is, suppose I take this particular thing, so this is inverted, I am taking 1, and this is -1. This is the product of these three, 1 into -1 into 1, which is -1. So to this state I assign the parity of -1. Some other state I have -1, -1, 1. So the product is 1. Okay. So here if you check, here if you observe, this has parity -1, while this has parity 1. 1 into 1 into 1, and this is -1 into -1 into -1, so parity is -1. So parities are different. And interesting thing is that the process of playing this game, parity does not change. And that's the thing. Why? Because suppose you have this state, so you have 1, -1, 1, you have -1. After that, whatever you do, you are actually doing minus, you are changing the position of 2, you are changing the configuration of 2. So you are actually multiplying with -1 square. -1 square is just 1. So you are not changing the parity in the process. And since the parity of this is different from parity of this, here parity is -1, here parity is 1. So we can easily conclude that you cannot obtain from this position all inverted position to all upright position. So the same question therefore had two different answers, one in terms of parity and one in terms of group actions. And interesting thing is that we can actually use groups to define various notions of parity. As I was saying in the previous lecture, the signature, the notion of signature in SN, that is also some kind of parity. So I am going to use that parity, and this kind of parity, Z mod 2 parity, this kind of parity, to solve for you some other puzzle, and somewhere permutations are there, groups are there. So today we saw how number of orbits, how calculation of number of orbits could be useful for some puzzle. Inverted glasses puzzle we understood. We understood it through group actions. We calculated orbits. There are two orbits. We explicitly could tell that they are two distinct orbits. Therefore, you cannot move from one configuration in this orbit to other configuration in other orbit. There is there are few more puzzles that we are going to discuss. So here is a puzzle which has to do with parity, and then we shall use groups to assign parity. So consider this. So I have this square, the tiles, 16 tiles, one corner is removed. Here is a similar set of tiles. The only thing is that there are two corners which have been removed from this. And it's a very simple question, extremely simple question is, I am given these kind of tiles, rectangular tiles, and the point is, can I tile up these things? So here there are 15, here are 14. Can I tile these things using these kind of rectangular tiles? So can rectangular tiles be used to obtain this shape and this shape? What would be your answer? It's not difficult. As you can easily observe, this has odd number of tiles, 15 is odd. So certainly you cannot tile up this using this, these are 2. So you are using some odd. What about this? Does it always mean that if the number of tiles which are here, they are even, and this is an even number, you can always tile it in this fashion? Well, it's not here. I'll put a question. But using parity, we could at least cross this possibility we could cross, right? So in various puzzles, actually keyword is parity. Parity is quite important keyword in puzzles. So what is parity? So you take actually all a priori possible configurations of a puzzle, or all possible situations you take, and then you assign to each of those configurations a number. It could be 0, 1. So one of these numbers, either 0 or 1, it could be -1 and 1, it could be a color, say red and blue, it could be. So what resolved in that previous situation, the case, it was this notion of parity, which was just take number of squares in the configuration. So in this configuration, number of squares is 15 mod 2. So 15 mod 2 is what resolved, even and odd, right? That was essentially parity. So even maybe we represent by 0, odd maybe we represent by 1. But this case could not be resolved using the notion of parity. What is interesting is that when you have some configuration, when you have some puzzles, it's interesting to see if while that puzzle is being played, while that game is being played, something remains unchanged. For example, in the case of 3 glasses, the parity remained unchanged. So parity was an invariant. So an invariant can take values in any set. Quite often the interesting situations are when this set is actually a group. So as I said, invariant is expected to be constant over the subset of plausible configurations. So if a game is being played, so all the plausible configurations are arriving, and it's an invariant, so certain thing is constant, some parity is constant. So over all those plausible configurations, the invariant is constant. And just being constant does not mean that your plausible configuration is actually there, is actually a reality. So we are going to understand all these things through an example. So in the case where two corners were removed, what can we do? We can use colors, and I am going to mathematically express that. So rather than seeing it like this, I could have seen it like this. And when corners are removed, this corner is gone, and when this corner is gone, if I want to tile it with tiles like this, then number of yellow tiles should be same as number of red tiles. But here I have removed both tiles which are red. So number of yellow tiles is 8, while number of red tiles is 6. So now it's very clear that if I want to use these tiles to completely cover this knocked off thing with 14 squares, I cannot, because number of red tiles is not same as number of yellow tiles. All this I would say in terms of parity, in terms of some invariant. So using the concept of color, yellow and red, this using the concept of parity, I have concluded that this is not plausible. So I cannot cover this, I cannot do this using these kind of tiles, it is impossible. So what was the invariant in this situation? What was the parity in this situation? So all these colors, all these colors which came to resolve this problem, I am going to express that through this expression. So tile ij is colored colored yellow if I plus j is congruent to 0 mod 2. So I plus j is having value 0 in the group Z2. Otherwise, it's colored red. And what is configuration X? Configuration X is tiles with these coordinates. I1, J1, one tile, other tile with coordinates I2, J2, they have been removed from the 4x4 that chessboard. And then if you define your number or the invariant associated to be I1 plus J1 plus I2 plus J2 mod 2, and that resolves the problem. And the observation would be that if fx is 0, then that particular configuration X is not plausible. So for example, if I knock it out, this particular one, then they are of the different color. So after removing exactly two tiles of different color, what you would have is that the number, the invariant that I have defined like this is actually 1. So then the question is, what configurations can be constructed from those rectangles that I had 1 by 2 tiles, those smaller rectangles, and answer is all. It's not very difficult. There is some graphs which are required to understand this, but I am not doing it here. So basically what I want to say is that the concept of invariants and some mod 2 invariants can be used to resolve certain puzzles, and here your function is lying in the group Z2. So we shall have some more interesting, some quite interesting puzzles later on. So I hope you enjoyed all this. So in coming lectures, we'll try to see more applications of groups. We will see 15 puzzle, we will see Rubik's Cube, and we will see how we can understand, how we can use our understanding of group theory to resolve the issues or resolve the problems which arise in those puzzles. Thank you.